dispatch times increased 10x because Cassandra's read repair returned stale tombstones for driver locations during a rolling upgrade. The matching service didn't check timestamp recency. Here's exactly why. First, let's understand the basics of Uber's architecture. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design Uber. Tombstone staleness is the accumulation of deletion markers that degrade read performance. In Cassandra, every update or delete creates a tombstone. Until Compaction reclaims them, every read must scan past these tombstones, increasing I/O and CPU. Uber operates a domain-oriented microservices architecture. Each domain owns its data and exposes APIs via an API gateway. Services communicate asynchronously through Kafka and synchronously through gRPC. The architecture is regionally isolated for fault tolerance. Here's the code that updates driver location in Cassandra. Each ping inserts a new row with a TTL of 10 minutes. Note the H3 index for geospatial queries. Uber uses H3, a hexagonal hierarchical grid. Each driver's location is assigned an H3 cell at resolution 9. The matching service queries the same cell and adjacent cells to find nearby drivers. TTL ensures old pings are eventually removed. This code queries nearby drivers by iterating over the hex ring cells. It uses a secondary index on H3 cell and epicmin for fast partition scans. When a rider requests a ride, the matching service filters eligible drivers, queries nearby drivers via H3, computes ETA and surge multiplier, then runs a second price auction to select the winning driver. The dispatch engine first finds nearby drivers, then computes ETA and surge for each candidate, filters those within 5 minutes, and picks the highest bidder with the rider paying the second highest bid. Surge pricing adjusts fares based on real-time supply and demand. A Kafka stream processor aggregates events per zone, computes the multiplier, and stores it in RIDIs. The rider app displays the surge before confirming. The surge calculator computes the ratio of demand to supply, applies an exponential moving average to smooth spikes, and broadcasts the new multiplier. Uber's payment system uses idempotency keys to ensure exactly once capture. For cross-region payments, a saga pattern with compensating actions prevents financial errors. The trip execution state machine runs on Kafka. This code checks if an idempotency key has been processed before executing the payment. If the key exists, it returns the cached result. If the network fails, it throws a retriable exception so the client can retry with the same key. Uber's system must survive data center failures and demand spikes. Key strategies include regional isolation, graceful degradation, auto-scaling, and regular chaos engineering drills. Circuit breakers protect downstream services. If the matching service errors exceed 50%, the circuit opens and a fallback returns cached driver data. This is the same issue we highlighted at the start. Here's exactly why that happened. During a rolling upgrade, Cassandra's read repair mechanism, combined with a long compaction backlog, returned stale tombstones for driver locations. The matching service wasn't checking timestamp recency, so riders saw drivers that were actually kilometers away or offline. The fix involved 3 changes: throttling read repair to prevent stale data propagation, adding a recency check in the matching service to discard pings older than 30 seconds, and moving to consistent reads with local quorum for the primary location table. If the Kafka topic lags, the surge calculation uses stale supply counts. This can lead to underpricing, no driver incentive, or overpricing, lost rides. Always use event time windowing and monitor consumer lag. This is the exact line that caused the incident. The matching service accepted any location ping without checking its timestamp. During the upgrade, stale tombstones were returned, and the service used them as if they were current. A common mistake is not checking the timestamp of the location ping. Even with TTL, Cassandra's eventual consistency can return stale data. Always validate recency at the application layer. A race condition in Saga coordination once paid a driver before capturing the rider's money. The fix is to use a transactional outbox pattern and process steps in order with compensating actions. The Tombstone staleness pattern described is most acute in Cassandra 3x and earlier. Cassandra 4, 2021, introduced improved compaction strategies and tombstone-aware queries that reduce overhead, but the fundamental problem persists for high update workloads. Always check your Cassandra version and compaction strategy before relying on tombstone mitigation alone. The article mentions monitoring tombstone scanned histogram, but doesn't show how to query it. Use NodeTool or JMX to retrieve per table tombstone metrics in production. The article recommends leveled compaction for high-delete workloads, but fails to warn that switching compaction strategies on a large existing cluster can cause severe write amplification and temporary performance degradation. Always test strategy changes in a staging environment and schedule during low traffic. To diagnose tombstone issues, check Cassandra read latency and the tombstone scanned histogram metric. Verify the timestamp of driver locations using CQLSH or RIDIs. Monitor matcher service latency percentiles. Let's run through some common interview questions. How to handle 5 Mbps pings S. Use Cassandra with TTL and H3 index buffer writes. Explain surge pricing algorithm. Multiplier equals demand / supply * target, EMA smoothed. Ensure exactly once payment. Idempotency keys plus saga pattern with transactional outbox. Trade-offs. Cassandra vs PostgreSQL. Cassandra for availability, PostgreSQL for consistency. And a few frequently asked questions. What is the primary challenge? Real-time geospatial queries at global scale. Why microservices? Independent deployment and scaling per domain. How does regional isolation work? Each region operates independently with DNS failover. What metrics to monitor? Matching latency, Cassandra read latency, Kafka consumer lag. To recap, Uber's architecture is a masterclass in trade-offs. Tombstone staleness must be handled at the application layer. Matching is a real-time auction. Surge pricing needs fresh data. Payment systems must be idempotent. And resilience patterns like circuit breakers are non-negotiable. Ready to go deeper? Up next, design Google Search, then design Amazon, then design Netflix. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.